Welcome all to the uh, ninth week of the class. I will wait for a few minutes so that the students may join, and then we'll start. Some 3-4 minutes. Yes. Hello. Okay, there seems to be some problem. Okay, we will start the class now. Uh, okay, let me present my screen. Just fine. You also fine. Okay. Okay, let us start with the new class. Today is week 9, and we'll continue with path integrals. Probably today or the next week, we'll do the end of the path integrals. And in path integrals, I'm strictly not following the uh, like the videos. I'm like what I want to say is I'm doing it as one does, starting from the path integrals in quantum mechanics, and then slowly go to field theory. Today we'll do some field theory path integrals, and uh, and then we'll go to and then we'll do some diagrammatics. It's yeah, we'll do some diagrammatics, and then we'll go to field theory, 5 4 theory, for. And I hope it gets continued in the the required time, because it's a very huge topic. Anyways, let's start. So we'll do scalar field theory today, and the simplest Lagrangian that we want to work with to understand the concepts is the Klein-Gordon Lagrangian, which is written as where phi means that phi of xy and mu, and our signature is this is important, 1 minus 1 minus 1 minus 1. This is the diagonal matrix. Okay. So the first thing to do is find the equation of motion, and that is easy to find, and you're going to get del mu plus del mu is written as this is written as del square. So what you're going to find is del square plus m square I is equal to 0. Here we have taken the units as 1, okay? C is equal to 1. Well, let me keep h bar. I'll just put C as 1 for now. Okay. So if you remember from last class, we find so we want to do some perturbative things, or we want to do some diagrammatics. And to okay, before going to the diagrammatics, let me just find Green's function for you. So you can write the field as the Green's function equation is del square plus m square times g is equal to delta. Now we have to be cautious in this. X comma x prime is equal to some okay, we don't have to find the Green's function here. There is 0. There's a delta function, so this is some j delta. It will become clear to you why I'm doing this. Okay, and I'm going to go to the Fourier space. The g can be written as g tilde omega e to the power I omega t omega e to omega and k Ah, I want to write in a very good notation, but I don't think so. Something in my mind. Omega t. So x minus x prime, I'll write as del x. This is just for notation convenience. This is del t is equal to is equal to j times integral of e to the power I omega e to the power del x is now this is with respect to x, not with the prime coordinates. D is dx, not dx prime. This is what I am to say here. And you are going to get integral, and there are appropriate stuffs here. The integral measure. I'm sorry, I've forgotten. 3k. So I'll write it as d4k. Similarly here, d4k. So you're going to get from here, you're going to get minus of omega square plus k square plus m square to j well, I need this. I'm kind of confused in the 4 minutes. Yeah, I need it. And also let me remove j from here. This j dependence will going to, okay, it can be there, it's not a problem. For this problem, okay, this is going to be jx. Yeah. So I'm going to write a shorthand notation here. Which is p mu plus m square. P mu should be p0 e square minus k square. So I should put a minus sign here. Is equal to Now this expression is true for every omega k. This means this for every omega and k are being integrated upon Saudi. So for every xt, therefore this should mean that it is the integrand itself is 0. Now for our problem, in our case, j of x is equal to 1. Therefore, Green's function is 1 by t square plus m square minus 1. Okay, let me see. Okay, there is some convention. Convention is put a minus sign here. This minus sign propagates. Minus sign propagates. Going to be like this. Okay, good. Good. So first you find equation of motion. So algorithm. So this will imply your x prime is integral for k of this thing and to the power I a delta x minus omega delta t. I'm going to put the minus sign below t square minus m square. This is what you're going to do. So the algorithm till now is first to find Green's function, first to find equation of motion, then Green's function. Okay. Now, function which implies your field solution. What I mean is you have to write. So this was 3. So this is number 4. Write your field in terms of variables. That is okay. For us, jy is 1, so it doesn't make sense. It's just jy is 1. So it's just the integral of this thing. Because it is easier in the case of this, which I'm talking about. But let us go to something else, and then you'll realize why I'm doing this. Okay. So I think I presented it rather badly. Let me And let me just take 1 minute. Let me just go over through where I want to go, what I want to say. Then I'll tell you. Yeah. Now we develop I think it will be too long. So the idea is to write a new Lagrangian, which has got your old Lagrangian. I discussed this in the last class also, plus some source term into your field itself. And the reason we are doing this is because when you're going to calculate, the path integral, when you're going to calculate the path integral, you're going to calculate z of j, and then you're going to put j is equal to 0 to get what you want. And the reason you are doing this is because you can, if you want to find 2-point function and all these things, it will be just coming as a something which I'll show you now. So consider action. This I had done in the case of quantum mechanics. Now what I'm doing is, the question is, you have the action as for a free field. You have this action. A, find the generating function. Then okay, solution. Z of j is nothing but integral d phi exponential of I by h integral of the action. Now here, what you're going to do is to write this part d mu phi as equal to del mu of phi del mu minus phi del mu. Okay. Then our z of j z0 of j becomes half del mu phi minus phi del mu phi minus m square phi square plus j phi. The first term is boundary term, and we are assuming that at the boundary this is 0. Phi at boundary is 0. So the first term vanishes, and you can club the second term and write it like this. Now this is equal to del phi exponential cut 4x del square plus m square phi. This is del square plus m square phi. But remember, del square plus m square phi is your equation of motion shall give you something. But we are interested in the we are interested in the fluctuations about the classical solution. So if you want to use, so see here, I want to incorporate the information that the classical equation of motion will give me this thing. Okay, sorry, will give me this thing. But to incorporate that, I can't incorporate it here. I want to incorporate. To incorporate this, we will do the fluctuations about the classical solution, and we'll write phi as plus some classical solution plus some fluctuations about it. Therefore, our integral which is this, becomes so phi classical will give j. So I'll write this as y plus equals plus by 2 j times um, j times del square plus m square. So this term will give me this term along with this term will give me. Now here is where I change phi to eta. I should have done it in this step only, but I'm doing it here. Step should not be there. No, I have a term of this sort. I'm going to write this as I'm going to again break it. This I'm leaving it intact. And these are total derivatives, so they won't contribute, assuming that the terms inside vanish on the boundaries. So we will get with this part, I'm going to get del square phi plus m square. So that is del square plus m square. So I'm going to get a j. Del square. So I have this whole, which is going to get inside j square del square phi plus m square. J, that is j times eta. Okay. Eta by 2 plus, that is minus eta del square plus m square. So this part cancels, and we're going to have j by 2 by classical minus eta by 2 del square plus m square. Yeah. So I'm going to separate this part now. This part is purely a constant. Oh, sorry. This part has a functional derivative on the j. Okay. So you have Okay, great. Now, this part is something, if you remember how we were doing it earlier. When I was showing you about the how taking the variation, I said that this will contribute towards the normalization. That this part I'm going to write as z of 0, okay, times exponential of, and the reason of saying that that is z of 0 is also very quite simple. If you remember, if you okay, here only, if you put j of 0 here, j of 0, j of 0, then this is 0, and you have nothing but this term. This is nothing but the same integral. This, so when j is 0, so you're going to have this, not have this term, and you're going to have only this term. And this is nothing but, this is the same thing as what we are getting now. And this part is j of 0, right? What we have in our equation is this phi is not phi now, it is eta, 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 and this part is not there. So this part is just j0 with 0, j subscript 0 with 0. So that is why this is j of 0, and there's the other part which is this, and this is this. Now this is the reason of finding the Green's function. This is the reason of finding the Green's function, because your phi classical can be written like this. So using this, so I'll just take it. I'm going to just substitute here this thing. Oh, this is x, remember, this is also x. Okay, with a factor of 2. I'm going to put it here. This minus sign, this minus sign, this minus sign comes from this minus sign. So we will get this. Now the reason, we also know what gx minus y is. Gx minus y, we found it. Gx minus y is nothing but this. Gx minus y is this. Okay. So now this can be written as, now, oh, sorry, now if you want to find, any, uh, if you want to find any correlation function, any higher point correlation function, you can just, the reason for finding this is you can just, this is our solution. The reason for doing this is its usability. perturbation series. What I mean by this is, if you want to find something like this, ix, iy, this is nothing but g of x minus 1. What you're going to do is, you just take del by del j, del 0 or j. You're going to find the, and then you're going to some series. You will have the action as Lagrangian as L plus perturbation, L naught plus L perturbation. You're going to modify it to L prime, which is L naught plus L perturbation plus J phi. Okay. You're going to do the procedure and to find the Green's function of perturb theory. Two-point function, you're going to do this and then put j is equal to 0. So we'll see this now. Okay. So let's go to okay. Before doing that, let us solve one problem. Find which is this term. I want to find this term. So this is the question. Okay, let us do it. So our WJ solution. So the strategy is to put and calculate, but so there is one strategy which I am going to tell you, which you might understand from the structure of this thing. So delta Q, I'm just writing, this is J1 plus J2 you have free Green's function. And you have this y as x1 and minus x2. These are fixed points. That's why they are x1 and x2. This is not y1 and y2. All right. So we'll just look at this term. Okay, there will be 4 terms here, which will be Dirac into 4 terms. Which schematically calling it as x1 x1 plus x2 x1 plus x1 x2 plus x2 x1. Okay. We'll start with the calculation of that x2 x1. From this, we'll see soon from the calculation we'll understand before this term is equal to the sum j12 is equal to minus 1 by 2h squared integral d4x d4y divided by the x minus x1 gf is nothing but gf of x minus y is delta d4k to the power 4 to the power I x minus y k I times square. Okay, one more thing. These are special positions. I forgot to mention. Now you're going to take this out. And you're going to do the Dirac integral. So you're going to remain with this thing. The d3x and d3y, it gets integrated. And you're going to have a term as such. So first integration will give you x1. The second integration will give you x2. Okay. Nothing has changed. Now we will also write this differently. So this is a 4 vector, remember. Even though I put a dot product in between, this means a 4 vector. So now I'll write it in terms of 3 vectors and this. So that is x1 minus x2 I minus I x1 minus x2 x1 minus x2 0 is 0. Now whenever we get integrals of this kind, we'll assume that x1 minus x2 can be written as some r vector, and this k is pointed towards say the z direction, and so we'll get the dot product as. So that means what I want to say is k vector is just z cap k cos theta. Okay. Means along the k vector, I have aligned my z axis. Okay. And this, sorry, and this can be written as some r. So the dot product between this is in spherical coordinates now. So the dot product in between them can be written as some r cos theta times k.
So dx0 dy0. And now this I am going to write as coordinate change. I am going to write it in, so this should have been one step. Okay, let me, okay, I won't take this first, I'll do this. There is an integral here which I missed. It is this integral. The x0 integral. So one of the integrals will give me Dirac of E0. Okay. So I've got this thing. Wait a second, I think I made a mistake somewhere. I just want to see. I think I made some mistake. Let me just check. Yeah, it is indeed a mistake. There is a vector sign. I should have changed it here. I x0 minus y0 k0. Okay, now I'm good to go. So there is no 1, 2 here. There was a mistake I was making. Okay, great. So yeah, this is correct. Now we'll do one of the integrals, dx0. Okay, we'll do one of the integrals e to the power ix, x naught k naught. This will give me minus 1 by 2 d3k. Right, now I've taken a Dirac delta from here. So this integral will give me dy naught Dirac delta of k naught. And I'm left with only I y naught k naught. Okay, by k square minus m square, where this k is like where this k square is k mu k mu. Okay, and remember this thing is so now I've got, and what I used here is just 1 by 2 pi q. All right, k naught naught. It's not here. D naught is equal to Dirac delta of k. This is the definition. Therefore, the above integral, now I'll do the integral over this thing, over k naught. And I'll get a dy naught. Now k naught, Dirac of k naught is 0. So I'm going to have I'm going to have it as 0, and the denominator will become k vector square s m square. Okay. So now in our convention, k vector square is ki ki, and this is a minus of k1 square minus of k1 square plus k2 square k3 square. This I'm going to call as k square, the mod of k square. Yeah. So this is like in momentum space. So 1, 2, 3. This is like the k square, the modulus of this vector. And now I'm going to do that one. That I'm going to go do an axisymmetric integral by saying that okay, let me first finish. So the above integral becomes, finally it becomes So first things, this k square will be k square now. And due to the minus sign, this minus and this minus, due to the minus sign, this minus and this minus will come out and cancel with this minus. So I'll have a total plus here and I'll remove this minus. So 1 by 2h cut. Now we will do axisymmetric integrals. Right? And we'll change coordinates in the momentum space. So x1 minus x2 is a fixed vector. Let me align it in z cap and with the modulus r. Okay. And k vector can be written in the spherical polar coordinate as this k, your cos theta, sin phi, x cap plus cos phi sin theta. Sin phi sin theta. Cap plus cos theta z cap. Therefore, the dot product of k vector dot x1 vector minus x2 vector can be written as r cos theta k. And d3k in spherical polar coordinates, d3k spherical polar coordinates will be dk, because there is no dependence of theta and phi in the integral. There is a dependence of no phi in the integral, so we are going to have this thing v a square sin theta, and from the d phi integral we will get 2 pi. And this is just minus I k cos theta k square plus m square. We'll put the limits, appropriate limits later on. By 2 pi square integral of dk k square plus m square times k square. Refers to the d theta integral. D theta goes from 0 to pi, and we have sin theta to the power minus I k r cos theta. With cos theta equals, cos theta is t sin theta, d theta is dt, and your dt, and your integral range is from 1 to minus 1. Integral range is from 1 to minus 1. But with this minus, we can invert the integral range and make it minus 1 to 1. So we will have h cap square integral of dk a square plus m square minus 1 to 1 dt to the power minus I k r t. So the integral will give us now. The reason is I've not written this as sine of kr. Can obviously write it, but there's a reason uh, because we'll have to do some contour integral here, and contour has to be shifted differently for this part and this part, and we'll come to know why. Okay. So I'm going to not write this now. I'm just going to write the integral. So I'll call this constant as f. Okay. Call this 1 and call this 2. I am. So now we want to do contour integral. And the integral of k is real from minus infinity to infinity. And so the contour goes as this. This is the real axis of k. This is the imaginary axis of k. And there are two poles in the imaginary axis. So how to close the contour? Whether we should close it up or close it down depends on what sign we have here. Okay. And the best way to check is like this. So you look at this term and write k in terms of real and imaginary part. What you're going to get is REK plus I plus k are so e to the power minus I REK c to the power minus I times I will give you 1, and so you're going to have imaginary k r. All right. Now, if this imaginary k, if you try to close the contour above, the imaginary k will be positive, and you're taking it to infinity actually. That means this portion will have an infinite contribution. So you don't close the, so you don't know how you are going to evaluate this part. Okay. This part has an infinite contribution. So the contour integral which you are going to do above, you don't know how to integrate. You don't know how to evaluate. But if you close the contour downwards, you're going to have a negative imaginary k. You're going to have negative imaginary k axis, and this term will nearly be zero. So the contribution from the contour is not very high. You're actually doing the contour integral now. So you're considering this contour, and it closes, and the contribution from this part plus this part is equal to the residue of the residue of the uh, residue of the integral. So residue of the function. So that means going to close the contour above the residue, the contribution from this contour plus this contour, you don't know how to evaluate the contribution from this contour. It is still going to be this plus this is still going to be residue, but you don't know how to evaluate this. So, but this plus this, we know this, the contribution from this contour is zero because of this term. That is why we're going to close the contour in this way. So I'll change this into a contour integral. I won't do any variable change though. I will write it as k still. Okay. And this is nothing but by I, residue of this thing is nothing but residue of this is nothing but uh, you're going to have to, this is a simple pole, so you remove one of the points and you put the value of the other one. That is to say, below your this term is zero. In this calculating the residue, you'll have this portion as zero. Remove this because this is a simple pole. Remove this and put the value here. So you're going to get E is equal to minus Im I e to the power minus I minus Im r minus 2Im. So you're going to get I e to the power minus, there is a minus minus mr by. This is how the integration will be. Now the integration of this part, in this part you have a plus sign here. So k and this will give you a minus sign here. Since there is a plus sign here, I and I will make a minus sign here. And now you have to close the contour above, and you're going to get the result as you're going to get will be 2 pi I plus Im. Now you're going to have to remove this term and put Im here. So it will give you 2Im to the power. You have a plus sign here to the power. So plus and Im will give you still minus m plus pi I by. All right. Now there is a small difference between these two integral. That is, this is in this direction. However, this is in this direction. The orientations of these contours are different. And to make the orientation same, you're going to have to introduce a minus sign by hand. Let us say that this is the proper orientation we want. So, and we're going to have to negate this so that we can have the proper orientation. So, in the integral which I am calculating, I'll put a negative of this expression, this result which I found. Therefore, I have integral to be f times I by m to the power minus mr minus of to the power minus mr. I'll get 2 pi I by m as it minus. So I'll put f now. 2 pi I by m. F is h. Squared h squared by the 2 pi cancels cancels. This is our solution. Now let us look at. So I told you about how you do it for 1 2, right? So now 2 1 2 1 will give you the same result, right? Why should it give you the same result? Because you're going to take the only difference which you're going to have in this integral is you're going to have now x2 minus x1, x2 minus x1 everywhere. But when you're going to take the dot product of x2 minus x1, you're going to have the same r. X2 minus x1 is r times z cap, and is r times z cap, and L is going to be the difference. So it will be r times the difference. So you're going to get yeah. So r times this thing. So you'll have a minus sign here. You'll have a, when you take the dot product, you will have r times minus z cap. and this will have a minus r kr, like minus kr cos theta. So you'll have a plus here, okay, and everything will be the same. Everything will be the same. The plus ikr plus ikr, you're going to have a plus, sorry. So it's plus ikr, so you'll have a plus here, you'll have a minus here, plus here, minus here. But now when you're going to do the contour integral, you are going to add it and orient in such a way that you're going to get the same result. Okay. So you're going to get the same result. So 4 into 2, this is for J2, J1. What about J1, J1 and J2, J2? In that case, you're going to have x1 minus x1 and this term vanishes. Okay. So whole of this term vanishes. This term is no longer there. So your contribution, and this term is also 0. This term is no longer there. So you're going to have just this. This term vanishes. So you don't need to do this integral. The integral which you are going to be, which is going to be remaining, is only this one. Sorry, this part. This is the best. No, yeah, this part is going to remain. Now what to do about it? What we can do is, so I will try to show that it is 0. So what you have to do is r goes to 0. Okay. So e to the power minus mr by r. So you have a 0 by 0 form. You differentiate, you're going to get minus mr power minus mr. So r tends to 0, 0 by 0. In this expression itself, r tends to 0, 0 by 0. So you do the L'Hopital's rule, and you do this thing. Going to get m minus m here, and you're going to get 1. Now take the limit, r tends to 0, you're going to get 0. R tends to, you're going to get 1. Well, this analysis is not correct in case of r tends to 0, it seems. So you'll have to do the integral and find out. But what you're going to find is that the contribution of this term, it does not contribute. That is what I want to say. So what you're going to be end up with is, so you're going to have this part. This is going to be integrated, and in the end, you're going to have this part. So you can do the axis symmetric integral now too. That you don't need any thing. You just change this, and you're going to have a squared sine theta k square plus m square. Now you truly have no dependence of theta, so it's going to be just integral of dk square by k square plus square minus infinity to infinity. So the integral of that, so you're going to be, so my claim is you end up with the integral of dk square k square plus m square minus infinity to infinity. In this integral, k square uh, k is equal to tan theta times m. So k is m6 square theta. The integral was from minus pi by 2 pi by 2 m6 square theta and theta m square and theta square cube k square plus m square, that is m square tan square plus 1 and tan square plus 1 is sin by cos 6 square theta. Just checking off. So this gets cancelled. We have this as equal to m square. Now tan 2 theta is tan theta 1 minus tan square theta. Just complicate as now. Sin square theta by cos square theta. Okay, clearly this won't be 0. The contribution will be, okay, one can find the contribution of that too, but it should come out to be 0 as far as I remember. Anyways, this is whatever it is. Okay, let us move to some problem in perturbation. So we saw that the free scalar field theory, I can write this thing to be the knot of J is equal to the 0, 0 to the power suppose this is normalized, so this is 1, and we'll expand this thing. So when we expand, we can write this thing as 1 minus by 2. Here I have taken h bar as 1. Now diagrammatic way of writing it. I by 2 pi to the power 4 a square minus m square is written like this. Whenever I have something like this, I have to write this. So if I have something like this, write this as like this. So z dot 0 j can be written as 1 minus half plus 1 by 2 factorial square. So we don't have a cross term here, no cross terms, no terms of this kind. Because it's not an interacting field. So that means I have written this in terms of one can verify this. one can check this. So the question is, verify the expression. This is, say, B expression alpha expression. Verify alpha matches with the third term which is this term along with these factors is with the no, let's do it for fourth term. Let's do an easy problem because there's not much time. Verify it matches with the second term. So this term matches. Okay. So that means calculate term x1, x2. And this is equal to Dirac delta g of x1, a of x2. I'll write this just like this. Now, exponential minus I by 2. Now this is a very compact notation which I'm going to use because I feel comfortable with it. G F G. Okay. And the integral. So I have not written anything, but what I mean to say is this term is exactly the same thing as before. You have to understand that there is a, when I'm writing this integral, there is dx dy present here. This is g of x, this is g of y, and this gf is gf of x minus y. Okay. This minus sign comes from I square, 1 by I square. This is 1 by I square. So this is equal to minus of, so exponential differentiation will give you exponential itself. Okay. So, and the first integral we are going to do over this j, this will give you minus I by 2 gf x2 minus y gy. All right. So the integral over uh, integral over x vanishes, so you have an integral over y. Same thing. You have minus I by 2 integral dx now. So you have gx intact, gf x minus 2. And you have integrated over using use this and then integrate it. Now we have to perform the differentiation again. So now there are two parts. So let's do the exponential integration. And the reason is the exponential integration will repeat itself. So that is by 2 g. It will just give me the same term. So I'm just going to copy it. All right. Now the other part. So for the other part, you are going to have exponential. So what I'm doing is the product rule. So I have this part and this part. So first I differentiated this part and I'll get the same thing as this part. Okay, but it will be x1 now, and I'll have one more. So I should rub this. Yeah. I'll copy the same part again. Yeah. And I need to change variables. So the x1. So plus the other part, when you differentiate, you're going to have exponential minus I by 2 g. So when you're going to differentiate this, we'll have a x1 here. So this will get integrated. So you'll just be ending up with gf of x2 minus x1 minus I by 2. Same here, you'll have x1 minus x2. And since they are so you're going to have this minus I by 2 gf of x2 minus x1 I by 2 gf of x1 minus. Okay. And Green's function is actually even when you change these 2 points. So this is nothing but minus I. So this will be added. You will have just minus I times. So this 2 will go away. I have added this. Start this part. So I am done with this. Now I have to take j equals 0. Okay. So when you take j is equal to 0, this part becomes 1, this part becomes 0, this part becomes 0, this part becomes 1. So you're going to get minus I times EF of 206. Now let us look in the series. The second term in the series is this, okay? And this is nothing but this term. This term. Okay. We are working with the series which is inside, okay? So we have actually got the right answer. Okay, now we are going to put this here. Put this in this expression in the second term of the. So now we are going to put what we got in here, and for the second term this is I square, and we had a minus sign, so minus minus cancel. This is gf x1 minus x2, and here I am going to have jx1 jx2. This I'm going to write this side, and I have integral of dx1 dx2, and this is the same as this. Okay, great. So verify. Now we'll start with some self-interacting field. And the Lagrangian, and these are scalar field theories. In the Lagrangian, one can write a general Lagrangian as this. So now, question: calculate dimensions G. Uh, one, G2, G3, and G4. D dimension. That is our phi is a function of D variables. So I'll do G4 and G3 is homework for you guys. So we'll start with the action. Action can be written as dx of Lagrangian density. And in the Lagrangian density, we have G3. So we need not be worried about other terms. We'll just worry about this term. Okay, then I'll also remove G3. I'm not worried about this term. I'm only worried about the G4. So when I set h bar is equal to 1, I make the dimensions of angular momentum as dimensionless. Action has a dimension of angular momentum. So this action is also dimensionless. Therefore, we have no dimension, which is 1. And we have d length dimension. This also implies that length is mass inverse. Okay. So we have d length dimension here, and we want to find mass dimensions. Means the answer should be written in terms of mass. So we have d length dimension, which is mass to the power minus d. And from the first term, we have mu, that is m to the power, and that is by x, that is 2. So d by dx, so we have m to the power, d by dx is L inverse, so we have that as m, and we have 2 of them, so we have m2. And dimensions of phi, which I'm going to write as phi to the power alpha. Alpha is the dimension of the field. Okay. So then phi to the power alpha is equal to m of 0. You can write this as m of 0, and minus d by 2. You invert it, so you're going to get d minus 2. So this is the dimension of your field. Now let us look at G4. So dimension of G4 times phi to the power 4, that is m to the power 4, is 4d minus 2. So there are two fields here. So this should be 2 alpha. So I'll have d minus 2 by 2. So 4 times d minus 2 by 2. Okay. This implies the dimensions of sorry. This the dimensions of that. So dimension of phi is d minus 2 by 2, and I have 4 times the field. So the dimension will be this is equal to, and now we have length. Now I have these many lengths, and they have m to the power minus d is equal to the power 0. dimension of G4 is equal to times m d minus 2 to 2d minus 4 minus d. 2d minus d. When I invert it, d minus 4, I will have this is the answer. Coupling, the coupling constant, the interacting constant, whatever, has a mass dimension of 4 minus d. It is marginal. That means it does not have any mass dimensions. It is dimensionless. Dimensionless coupling in d equal to 4 dimensions. So this is special. So 5 power 4 theory is kind of special in 4 dimensions. That is what I wanted to conclude. So you can find the mass dimension of G3, and we will do some perturbation 5 power 4 theory, some perturbation Green's function we'll look at in the next class, and then we'll go to the next topic. I think path integral till here is all done. So that's all for today. Thank you for attending the class. I'm ending the meeting.